Black holes, among the most bewildering and exceptional phenomena in the universe, continue to be a subject of remarkable analysis and captivation for theoretical astronomers and scientists. Similar to these astronomical objects, characterized by their immense gravitational strength and the complete absence of emitted light, they signify a threshold where established principles of physical science cease to function. Originally hypothesized by Albert Einstein in 1916 as a result of his general theory of relativity, black holes remained purely hypothetical until modern technology enabled their indirect observation. In the 21st century, in the 1960s, a turning point occurred when researchers examining the Cygnus constellation inadvertently identified a peculiar stellar body, a radiant blue star releasing intense X-ray radiation. This star, stuck in an orbit with an unidentified partner, resisted conventional explanations until it was determined to be gravitationally bound to a colossal black hole known as Cygnus X1. The Cygnus X1 detection provided tangible proof of black holes' existence and ushered in a transformative phase of the study of these cosmic mysteries. Situated approximately 6,000 light-years from our planet, Cygnus X1 possesses astonishing traits. It is extraordinarily compact and produces a gravitational influence so powerful that even photons cannot escape. This hallmark feature led to the name black hole, effectively capturing the essence of these enigmatic structures. Subsequent investigations have identified an assortment of black holes dispersed throughout the universe, with projections indicating that our Milky Way galaxy alone could contain over 100 million such objects. Despite the fact that their properties complicate direct observation, astronomers have recognized numerous potential examples within our galaxy, ranging from stellar mass black holes originating from the collapsed cores of enormous stars to supermassive black holes residing in galactic centers. The gravity exerted by black holes affects more than just the area around them, influencing the development of universal structures and adjacent matter that too closely approaches. A black hole meets a fate governed by its unyielding gravitational power. It is gradually dragged toward the event horizon. It's an ultimate barrier where it undergoes extreme gravitational stretching and is ultimately absorbed by the singularity at the center. This dramatic process, spaghettification, is the ferocious result of the gravitational pull of a black hole's dominance. As an object nears the event horizon, the difference in gravitational pull across its structure becomes so extreme that it is elongated and deformed into a thin strand resembling spaghetti. The gravitational forces surpass the cohesive bonds, holding the object together, disassembling it into a stream of particles that ultimately integrate with the singularity. Though black holes present an extraordinary opportunity for examining the extremes, they continue to be shrouded in mystery. The effort to decode their nature persists, fueled by a longing to comprehend the core aspects of space-time and gravitational mechanics. Amid the vast expanse of the cosmos, black holes stand as quiet guardians, inviting humankind to delve deeper into the unexplored and broaden the frontiers of comprehension. Despite the immense remoteness from the nearest black hole, approximately 1,500 light-years away, questions and apprehensions regarding their possible effects persist. In 2021, scientists made a groundbreaking stride by acquiring the initial final, the image of a black hole, specifically the one at the center of galaxy M87. This extraordinary feat delivered pivotal knowledge about black holes and their elusive form. The images captured revealed that black holes consist of intricate layers, confronting the previous notion of them being isolated voids of absolute emptiness. Through detailed study and image compilation, researchers distinguished three specific layers within a black hole. The outermost is the event horizon, a crucial boundary that denotes the limit beyond which return is impossible. Once something passes this threshold, gravitational acceleration becomes unstoppable, sealing its plunge into what lies within the black hole's depths. Inside a black hole, progressing inward, the photon sphere forms the second layer, a zone where light orbits the black hole endlessly. Any photons entering this area are overpowered by gravitational influence and remain eternally confined within the black hole's grasp. At the very center exists the singularity, the final and third zone, where physical laws disintegrate. The familiar principles that govern space and matter collapse, ushering scientists into a domain of vast ambiguity and theoretical speculation. The inherent complexity and diversity of black holes pose major hurdles for scientific interpretation. Even though many share a common three-layer model, each black hole's distinctive properties and actions evade straightforward classification. Consequently, traditional scientific methodologies often fall short when exploring these immense cosmic phenomena, demanding inventive and novel techniques for uncovering their truths. Since direct research is impossible due to the overwhelming constraints caused by gravity, indirect monitoring remains the main approach for studying black holes. Any mission attempting to deploy instruments into a black hole would face inevitable obliteration by the extreme, persistent gravitational environment. The research continues to seek understanding of these astronomical titans. Numerous hypotheses, from stellar collapse to dynamic cosmic evolution, provide captivating insights into their origins and nature. NASA's observations of the central region of M87 uncovered convincing indications of a supermassive impact caused by a massive black hole. Despite numerous difficulties, the drive for discovery advances, fueled by the inherent human urge to explore and explain. Although black holes may defy basic comprehension, the unwavering dedication to scientific discovery holds promise for unveiling the universe's darkest secrets. Roy Kerr's groundbreaking findings in 1963 introduced a game-changing view of black holes by proposing a model of rotating black holes that challenged accepted doctrines. A cornerstone of Kerr's theory was the ergosphere, a surrounding region where opposing forces neutralize total gravitational collapse, keeping matter from plunging further. Inside this peculiar area, extraordinary deviations from normal physics point to the deep puzzles buried beneath black holes. Perhaps the most captivating outcome of Kerr's hypothesis was the suggestion of an Einstein-Rosen bridge, or wormhole, a speculative construct that could link distant regions of space, or even parallel realities. The wormhole concept emerges from the sophisticated relationship between reality and the principles, defined by general relativity. In this vision, reality is woven into a four-dimensional tapestry called space-time, with mass-warp distortions. Creating gravitational effects we observe, wormholes are essentially shortcuts through this vast fabric, potentially joining widely separated locations in space and enabling rapid transit across the cosmos. Cosmos stills, the reliability and usability of the structure, continue to divide physicists. While wormholes open up thrilling prospects for interstellar voyages and temporal experimentation, serious barriers and theoretical inconsistencies temper these hopes. Visions of their fragile nature, along with challenges from quantum theory and radiation, cast doubt on their function as viable means of transportation. Furthermore, general relativity sets hard restrictions on travel speeds through space-time, implying that, even if wormholes existed and were stable, they might not allow travel faster than light, a hallmark of science fiction. Despite this, wormholes continue to inspire scientific inquiry. Their very notion, named after foundational theorists, embodies the thrilling idea of universal passageways and alternate dimensions, sparking humanity's imagination about the broader cosmos and its infinite potential. The ambition to forge a single, unified explanation that bridges the gap between gravitational theory and quantum mechanics has led scientists toward a theory of everything, a total model that encompasses all elementary forces and particles. At the head of this mission is the celebrated physicist behind M-theory, whose pioneering research has advanced superstring theory. This theory represents a significant shift from conventional paradigms by proposing that elementary particles are not tiny dots, but minute vibrating strings. These strings, similar to those on musical instruments, vibrate in distinct frequencies, generating all known matter and forces. In this view, the universe resembles a grand composition, with each particle symbolizing a specific tone of these elemental strings. Superstring theory may also illuminates some of the most puzzling features of black holes, wormholes, and other exotic elements within Einstein's gravity equations. The oscillation of strings through spacetime contributes to the emergence of singularities and topological oddities. Despite its beauty, superstring theory is extremely complicated and requires the existence of extra dimensions beyond the familiar. 3 spatial and 1 time dimension. These hidden dimensions, not directly observable, challenge human perception. To illustrate their elusive nature, analogies like fish living on a 2-dimensional surface help explain how beings in a limited dimension might be unaware of higher spatial planes. It is believed that these hidden dimensions are compactified or curled up, making them undetectable in daily life, yet they profoundly affect physical phenomena. Though their exact character remains undetermined, their theoretical presence offers valuable explanations for the universe's strange behaviors. Additionally, the mathematical foundations of superstring theory have sparked a revival in theoretical physics, showing connections between the intangible and the abstract. Indeed, the drive to find a universal theory of everything has unified various scientific fields, highlighting the deep relationship between numbers and natural laws. Despite this, superstring theory still awaits experimental support, as its predictions are hard to test due to the invisibility of higher dimensions. Even so, the bold vision of superstring theory continues to enthrall scholars and dreamers, urging humankind to pursue intellectual growth and cosmic insight. As we progress through modern physics, guided by this luminous theory we stand on the edge of deeper knowledge and awareness. Decoding the puzzle of quantum black holes has long baffled researchers and remains one of the greatest mysteries in physics. Despite countless attempts to resolve this conundrum, complete answer has proven elusive. Edward Witten, from Princeton's Institute for Advanced Study, famously called superstring theory 21st century physics that accidentally arrived in the 20th. Yet relatively recent developments have reinvigorated hope. Multiple teams have independently revealed significant progress. It's indicating that string theory might indeed offer a full solution, though. For now, it's restricted to simplified models. In 2 dimensions, instead of the 10-dimensional structure normally proposed by the theory. Despite the significance of this advancement, a full resolution is still pending due to the complexity of the issue and present major obstacles. The ongoing journey toward a unifying theory calls upon us to explore the farthest reaches of the cosmos, where the line between fact and theory blurs and profound revelations await. The study of black holes is very important to our understanding of the universe, challenging core beliefs about reality and provoking philosophical reflection. The processes behind black holes and other astronomical phenomena such as gamma-ray bursts and neutron stars unveil the delicate mechanisms shaping the structure of the cosmos. These energetic stellar collisions are not merely random, serve as insightful markers of cosmic behavior, showing how gravity, matter, and energy interact on scales far beyond human experience. Black holes, once thought to be theoretical oddities, now play a central role in explaining the dynamics of galaxies, star formation, and even the evolution of the universe itself, as scientific instruments grow more advanced from gravitational wave detectors to space-based telescopes. Our ability to observe and investigate these enigmatic objects improves. Discoveries like the detection of gravitational waves, ripples in spacetime caused by black hole mergers, have validated long-standing predictions that introduced a new frontier for astrophysical exploration. At the intersection of observation and theory lies the continued attempt to merge Einstein's general relativity with quantum mechanics, a challenge that black holes uniquely embody. These cosmic singularities present conditions where both sets of rules must apply. Scientists are now compelled to reconsider the fundamentals of both disciplines. Black holes, wormholes, and the space-time fabric they manipulate may eventually provide the key to unlocking a more comprehensive model of reality, one that seamlessly includes quantum field theory and gravity. Until then, there remain both puzzles and promises, prompting continual inquiry and arousing the imagination of a new generation. From string theorists to Einstein, from Hawking to observational astronomers, The story of black holes reflects the ever-evolving quest to understand our place in the universe. With every equation, simulation, and image captured, we come closer to unraveling not just the secrets of these cosmic powerhouses, but additionally, the fundamental character of existence itself.